Rachel wanted a chocolate tempering machine, which is basically a hot pot with really precise temperature control, but those cost hundreds of dollars. But I found the cheap one. But the temperature dial on this one doesn't go low enough, and it's also not precise enough, so I thought I'd try hacking this one. To make sure I could get the electronics to work, I wired up a Pi Pico with a temperature sensor, a solid state relay, display, and buttons. And right now it's switching the solid state relay on and off from time to time, which right now just switches this light on and off. And the solderless breadboard that everything's plugged into is from busboard.com. They sent me this one. And the nice thing about these ones is if you cut the thing on the back, you can detach things like the ground leads, because if you plug something like a Pico in here, you don't have a lot of pins to plug in on there anymore. But with the power leads disconnected, I could put this one on here and essentially have this straddle two breadboards. I decided to just have these hanging off the edge because I've got enough I/O lines on this side. But that feature is really handy if you're using something like a wider ESP32, where if you plug that into a breadboard, you really have no room to connect on one side at all. I was going to just have a temperature sensor that goes in the chocolate, but Rachel didn't like that idea, so I have to sense the temperature from the bottom somehow. And turning this one on and checking it with an infrared camera, it looks like there's only a hot spot in the middle, although we get lots of reflections, so let's just dump a little bit of water in here. And we very much have a hot spot in the middle, so it doesn't seem to spread the heat around very much. So maybe if I use this piece of aluminum as a heat spreader, and again I'll put some water on top so we can see the heat better. And that also couples it to the bottom very well. And that does a better job of spreading the heat, though not as well as I'd like it to. Let's have a look inside of this thing. So here's the heating element with nothing to spread the heat out, and this is the temperature sensor thing for the mechanical thermostat. Oh, that's stuck on good. There we go. So my idea is to put a heat spreader down here with a heating element on it and a temperature sensor in it as well. But I'm not sure if this is thick enough, and I've got this other piece of aluminum, which unfortunately is cast aluminum, so I'm not sure how good this is, so let's try it out. So this is the aluminum plate on the heating element with a wet piece of paper towel on it so I can see the infrared. And here's what the heat profile looks like. Doesn't look too bad right now. And here it is after a minute. And here's my other piece of aluminum after a minute, and I think this might actually be a bit worse because I'm seeing a bigger temperature difference from the middle to the edges after a minute. And I've read that the thermal conductivity of cast aluminum may be significantly lower than rolled aluminum, and that appears to be the case here. It's because of alloying and potential porosity in the material. So my plate is going to go in here like this, but to prevent the heat from this to feed directly into the pot and make a hot spot, I'm going to mill away a little bit of material where it touches this part here so that we don't get the hot spot coupling straight through. Not pretty, but it did the job. Now that display and the buttons are too small and fiddly to make a nice front panel by hand, so I started by modeling it in SketchUp. And with the shape of these two objects, I designed a front panel to fit around them. And these cavities fit around those objects, and each of those cavities is an object called mill something or other. And I run my complicated Python script on the 3D model, and it shows me the tool paths that it's going to generate for that. And then I mill it out on my Carrera Air. And I have to say, if I had a 3D printer, I would probably 3D print that. But going this way, my material costs are practically zero, and I can iterate a lot faster because this will mill a lot faster than a 3D print. And the rubber around the edge I just cut with a table saw because it's faster and it makes it much easier to mount the workpiece if I don't cut to the edge. So after a little bit of handwork, it looks like this. And there's a little screen protector goes in here, and the display in here, and the button board right here. And that's going to mount right here, so I just need to make a hole for it. And now I just have to precision cut that hole. Now to mount everything, the heating element is going to get pressed against this plate. The temperature sensor goes in this slot in the plate. Of course, the buttons and the display are on here, and I think I'll just mount the Pico to this, somehow to the front, to whichever piece of wood that's going to squeeze these two in place, and that goes in here. That leaves the solid state relay and the power adapter to get the 5 volts for the Pico. And I figured that is going to go on the side here with the screw from the side, and that will also mount the solid state relay. And I'm just bonding my heat spreader with a thin layer of caulking. I figure that should do because it'll never get really hot. And then the heating element, also with caulking. So I got all my circuitry wired in here. Now this just needs to go in like this, and it needs to be held in somehow, and for that I made these little things to screw onto the back here, which will pull the front panel against the hole. I wrote the program for it in MicroPython. I spent a lot of time tweaking the user interface. It's kind of fun to figure out how much I can get onto that small 128 by 64 display. It's almost the same resolution as the original BlackBerry, which was 132 by 65, and back in the day, we did a lot with that resolution. Now, because I'm only sensing the temperature of the plate, I want to have good connection between that and the pot, so to just dump a little bit of water in there makes for a much better thermal coupling. And let's put a few chocolate chips in there to melt. And set the temperature to the melting temperature. And we haven't reached the set point yet, but I'm cycling the heater on and off once in a while, because there's essentially a little bit of inertia, because where the heater is different from where the sensor is. So if I heat it right up until the set point, it'll way overshoot because it takes time for the heat to get from the heater to the actual sensor. And so it slows down as it approaches the set point to avoid overshooting it, which I'm not sure it makes much sense because the temperature of the chocolate in the pot is going to lag the temperature of the plate and the sensor anyways, so overshoots might not matter. And as we approach the set point, I have a little bit of temperature oscillations, which I've learned to accept because you want to be able to approach that set point a bit faster. And with the temperature in the pot lagging anyways, I'm just going to bump up the set point a bit to actually get it to melt in there. And we're just a bit past 46 on the plate, and looking in here, at least this one is melted. And when people melt the chocolate, to make sure it all has the same temperature, they just stir it and apply more heat. So my idea of hitting the hot plate with exactly the right temperature, that would just take way too long. Plate is now at almost 49 degrees, where it should melt at 46, and these still look like chocolate chips, but let's just check. Oh no, these are actually pretty liquid. It's just a non-Newtonian fluid, so they don't necessarily just go blup like a water would. And chocolate tempering means after you melt it, dropping it down to 27 degrees where it's still kind of gooey, and then bring it back up to 35 degrees, and then when it cools from that, it turns out nice and crispy and hard. So let's drop the set point to 27. And it's taken about 25 minutes to get there, but we're now at 27 degrees, and every once in a while it turns on the heater just briefly to maintain that temperature. And now set it to the 32 degree working temperature. And here it's carefully approaching the set point that's shown in solid, trying not to overshoot that too much. And at that 32 degree working temperature, it hasn't undone the temper, and I can dip solid chocolate in there without melting that part. And now dumping some pistachios in the rest of it. I'm really just farting around experimenting, but Rachel's been making some really delicious chocolate truffles without a machine, and this machine will make it a little bit easier just because it controls the temperature on its own. And the whole point of tempering is that the chocolate, when it solidifies, ends up nice and crisp and hard like in a chocolate bar, not something that is soft.